Did I lose my bag? I had my bag there. Has somebody kept it somewhere? Or?
I'll check.
Yeah, no worries. Okay, so I hope you had a good tea session. No, that's not mine.
It's a laptop.
Laptop. Oh, पीछे रख दिया. Okay. No, that's fine. Yeah, okay. Right. I hope you had a good tea break. What did they feed you? Samosas and biscuits. Good show. Yeah, that's very good. I just had tea because normally, I don't know how many of you are lecturers, but if you want to teach, you don't want to have a heavy stomach, right? Yeah, you want to feel light and energetic rather than sluggish. So that's the reason I just had a cup of tea. So that's nice. Tea here is fabulous. It always is good. So let's continue our discussion. We have just talked about the calculation of reliability for series systems, parallel systems, and some combination of them. Series, parallel, parallel series, and things like that. And eventually we arrived at some conclusions. And then we also went to what we call as partially redundant systems. That means only 2 out of 3 or 2 out of 4 components are required for system success. So we have seen how to calculate the reliabilities and unreliabilities. Now we use the number, as I was mentioning, 0.9, 0.8, whatever came from, right? So slowly we are moving in a direction whereby we say, hey, that number may not be a single number. Maybe it is obtained by a probability distribution. So that's why we are now going to talk about probability distributions in reliability analysis, okay? So in actual practice, the parameters associated with the reliability are described more by probability distributions rather than by just a number or an average value, okay? And you know, all the components of a given type usually won't fail at the same time. I mean, if there are 10 people who buy a TV, let's say on the same day from the same shop, yeah, all the 10 TVs won't fail in 1 year's time, right? Maybe one will fail, the other one will fail 3 years down the road, things like that. So even if you have 10 identical components, yeah, they will all fail at different times, which tells you that the failure is described by a probability distribution rather than, you know, it is a constant, isn't it? So that's why we need to know about these probability distributions. So this probability is therefore a function of time, because in reliability calculations, a random variable is frequently time. And of course, yesterday we talked about 2 types of distributions, discrete and continuous. Examples of discrete are binomial and Poisson, and examples of continuous are normal, log normal, exponential, Weibull, gamma, Rayleigh, and so on. Don't worry, I'm not going to go into too much detail. This can get highly mathematical. Yeah, we have studied all these, but honestly for this course, I think the exponential is probably the most important, followed closely by the normal or Gaussian distribution. So I'm going to take you through those 2. Start with binomial distribution. So binomial distribution is directly associated with the type of problems that we have discussed so far. Yeah, the main thing about binomial is that we should know all the possible outcomes. So for example, if you toss a coin, you know that there are only 2 outcomes. You toss a die, you know there are only 6 outcomes. So for generators, transmission lines, feeders, distribution feeders, we know they are either operating or not operating, right? Of course, some of them may have what we call as derated states. I mentioned this yesterday, and I also told you that we usually do not look at a 14-state model because researchers have already studied it, and they found that a 3-state model is good enough. The up state, the down state, and the middle state, what is called as the derated state. As long as you have sufficient data to know the probabilities of being in each of these 3 states, then you can use them for your reliability calculations. The main hurdle is always the data. Is there sufficient reliability in the data itself? If the data are not reliable, your analysis can never be reliable, right? Yeah, 2 wrongs don't make a right, as the saying goes, okay? So for binomial distribution, we need these 4 conditions to be met, where P is the probability of success, and Q is the probability of failure, and N is the number of trials. there must be a fixed number of trials. So we need to know n, 10, 20, 100. Each trial must have only these two outcomes, P or Q, system success or system failure, where P plus Q is equal to 1. The values of P and Q must remain constant in each trial. So every time you throw a coin, the probability of getting a heads does not change, right? So these must remain constant. In a second time, they are not dependent on each other. They are completely independent. So those are the conditions for the binomial distribution to be applicable. I'm sure everybody has studied binomial at some point in time. So this is the expression for binomial, P plus Q to the power of n. You can expand it like this and then calculate the probability of exactly R successes in n trials by using this equation, which ultimately boils down to this: NCR, C stands for combinations, P to the power R and Q to the power n minus R. 1 minus P is Q, right? Remember we said there are only two outcomes, P plus Q is equal to 1. So if I know P, then I know Q. So from the above equation, all these, submit all these, and ultimately of course it should be equal to 1. So examples always help us to illustrate what we show mathematically. So we toss a coin 5 times. Find the probability of each possible outcome, meaning probability of 1, probability of 2, probability of 3, yeah, where P is the probability of getting ahead and Q is the probability of not getting ahead, which is of course getting the other option, which is the tails. And R is the number of times a head appears. So we want to find out the probability of 1 head, 2 heads, 3 heads, 4 heads, 5 heads. That's our objective using the binomial. So P plus Q to the power 5. Why 5? Because we have got 5 trials, right? Yeah. That coin is tossed 5 times. We've got 5 trials. So R is 5. So 5's NCR, P to the power R, Q to the power n minus R. Yeah. So we start with R equal to 0, then R equal to 1, R equal to 2, R3, R4, R5. Clear? So we can use this to find the probability of 0 heads. This is the probability of 0 heads appearing. This is the probability of 5 heads in 5 tosses, right? So each of these probabilities you can find. In fact, this equation can be simply written by expanding P plus Q to the power of 5, and that's given by this particular expression. So another example, if 1% of a particular product is known to be defective, 1% is known. So for example, if you have got 100 items of a product and it is known that only 1 out of 100 will be defective, then that probability is 1%, right? What is the probability that a customer buying 50 pieces of the product at random will get at most 2 defective pieces? At most. That means none defective, 1 defective, or 2 defective, right? That's what we mean. So let the probability of defective piece be 1%, 0.01. Therefore, the probability of not being defective is the complement of that is 0.99. So probability of 2 or less defective is 0 defective, 1 defective, 2 defective. So probability of R equal to 0, R equal to 1, R equal to 2, and that's your binomial distribution, yeah? So we can calculate that particular probability. So this is the probability of 2 or less defective pieces, yeah? If he asks you the probability of 3 or less, 4 or less, then you can easily expand the binomial and find out the number. Another example, probably a more practical one. An aircraft landing gear has 4 tires. That's typical. Yeah. Experience shows that tire bursts occur on an average on 1 landing in 1200 landings. Fairly practical question. Assuming that the tire bursts occur randomly and are independent of one another, and that a safe landing can be made if not more than 2 tires burst out of the 4, what is the probability of an unsafe landing? Yeah? Question is clear, right? Once you read, you know what data is given, what is asked of you. So the number of tires, n, is 4. P is the probability of a tire bursting. Yeah, 1 in 1200, right? So that's the probability of tire bursting, and the probability of tire not bursting, that means the success, you don't want it to burst, it should be high, right? Cannot be the other way around, right? So we use P and Q depending upon the problem. You may call this Q, you may call this P, because normally we use P for success and Q for failure, right? In this case, we are using it in the opposite way. So as long then it should be fine, yeah? There's no hard and fast rule that P must always be success, Q must always be failure. It's up to us how we define them. So probability of a safe landing is the probability that not more than 2 tires burst. So 0 tires, 1 and 2 tires bursting. So P of R equal to 0, P of R equal to 1 and P of R equal to 2. So this is R equal to 0. So NCR, P to the power R, Q to the power N minus R. So 4C0 and P to the power 0 is 1, of course, and Q to the power of 4. So that's the number. And similarly, you can calculate the 3 numbers. The probability of safe landing is this much. So the probability of unsafe landing is 0.40133, because that's what the question asked. What's the probability of an unsafe landing? Okay, clear? Right. So we have just showed you how the calculations come into play when we have the probabilities that are distributed according to a binomial distribution. But of course, not all events can be described by a binomial distribution. So we must look at other possible probability distributions. And for that, we need to go back to continuous distributions, because all the other only binomial and Poisson distribution are examples of discrete distributions. Now we are getting into continuous. So we will be looking at exponential, gamma, Gaussian, Rayleigh, Weibull, and all those. But we'll restrict ourselves mainly to exponential, but I will also share a little bit about the normal distribution, which I'm going to use, I think, on the 3rd or 4th day to illustrate to you when we do generation calculations. Then we will use the normal distribution as well. Sorry?
In industry, mostly Weibull 2 parameter.
Yeah, so depends on your application. We can also use the Weibull. I'm not saying that Weibull is no good. See, these Weibull, normal, Gaussian, they are all 2 parameter distributions. You need 2 parameters. Whereas exponential distribution is a 1 parameter distribution. You only need the failure rate or the repair rate. So we always start with the one that is simpler. Secondly, most of the failures in power systems, they can be described by an exponential distribution. So that's why this is the most critical for us. Yeah. No reason not why you can't use Weibull for repairs, not for failures. Failures are primarily distributed by exponential distribution. So that's why we discuss the exponential first. Okay? So you remember the cumulative probability distribution function from yesterday, or have you thrown it out the window? Cumulative probability distribution function, we spoke about it yesterday, right? We said there is a probability mass function for a discrete variable, yeah, and then for a continuous variable we have got a probability density function, PDF. Yeah, we use that word PDF, which in day-to-day life we use for a different purpose. And the cumulative function is called cumulative probability distribution function, yeah. This is the cumulative function which goes from 0 to 1. If it is a discrete random variable, it will go in steps. It will go in steps. If it's a continuous random variable, it's go in the form of a curve all the way asymptotically, and it will approach 1 unity, right? So we have already seen that. And then in reliability calculation, the random variable is frequently timed. So if we say that at t equal to 0, the system is operating. If we say that now, I'm starting my event now from this moment, and at this moment I say t is equal to 0 and my system is operating, then the probability of failure at that time is 0, isn't it? System is operating at this point in time, I'm here at this point in time. And then I say as my time goes to infinity, clearly my system is going to fail. Yeah, it's not going to be up forever, it's not going to be operating forever. So we can therefore use this characteristic as a cumulative distribution function, and we get the probability of a failure as a function of time. Yeah, so this function is called as QT, cumulative failure distribution function. And the complement of this function is called the survivor function, and we designate it as RT. Now obviously by now you are familiar, R is reliability, Q is unreliability, right? So what does it look like? So this is what the QT looks like. Remember I told you that at time t equal to 0 it is operating, and as t goes to infinity it will fail. So the characteristic for QT is going from 0 to 1. Obviously the characteristic for RT is going from 1 to 0. It's just the opposite. The survivor function RT, yeah, both are functions of time. So RT is 1 minus QT. The failure density function in this case is minus d by dt of QT, yeah, probability density function if you remember, and then we can differentiate this using QT is equal to 1 minus RT, and we'll get this particular equation. QT is integral 0 to t ft, and RT is 1 minus QT, yeah. So these are some of the standard equations that we get. The total area under the failure density function must be unity. We also mentioned that yesterday. So the reliability function RT is actually going from t to infinity f of t dt, because 1 minus 0 to t is as good as t to infinity, right? So we can integrate from t to infinity of the function f of t. That will give us the survivor function. Now this QT and RT curves that you saw just now, they complete the discussion on our terminology, but we also want to introduce another parameter written as lambda t, yeah, as a function of time. Everything is a function of time now, okay? And this is defined as the number of failures per unit time over the number of components exposed to failure. Now this hazard rate, if you look at the next graph, it looks like this, and this is the famous, or depending upon your perspective, you may call it the infamous bathtub curve. It looks like a bathtub, right? So that's why the name given to it. And in electronics, if you have studied more of electronics, then you will know that this little phase 1 is called the debugging phase. The phase here, phase 2, is the normal operating life of the component, and phase 3 is what we call as the wear out phase. So in the first phase, some components will fail because it's, you know, incipient failures, design failures, and therefore we call it the debugging phase. And most of the components will continue to operate, and this period is the longest period, the normal operating life of the component. And then once it starts to wear out, then the failure rate goes up, the hazard rate goes up, right? So this is the period that we are interested in, where the hazard rate is a constant, and lambda of t is actually just equal to lambda. If it is a constant, means it's a number, right? Yeah, then it is not described by a distribution. So that's the one that we are going to use in our exponential distribution. So exponential distribution, the hazard rate is called the failure rate, and it is a constant because we are dealing with the useful life period of the component rather than the debugging phase or the wear out phase. Okay? So we'll simply use the constant failure rate called lambda instead of lambda t. The exponential distribution is widely used in repairable systems, and as I mentioned earlier, data suggests, research suggests that failures in electric power systems are exponentially distributed. Repairs are not, but failures are. Repairs can be described by other distributions, as he was mentioning, by Weibull or normal and other types of distributions. But failures, as states, this expression e to the power lambda t, and assuming lambda t is a constant, then of course it can be replaced by simply lambda. So using the exponential distribution, it's simply e to the power minus lambda t, where lambda is the failure rate during the operating life or useful life of the component. Okay. We already know that this is the most valid when lambda is constant. If lambda is not constant, then you cannot use the exponential distribution. So we can write some more equations, but really the most important thing for you to realize is this one. Yeah, r of t is e to the power minus lambda t. Therefore, q of t will be 1 minus rt, right? Which is 1 minus e to the power minus lambda t. So those are the equations that we are going to use. We can also calculate the mean and standard deviation of the exponential distribution. Yeah, so the mean, if you recall, is given by this. Yeah, and for the exponential distribution, we can write it as t times instead of x, t times instead of fx is ft, and therefore if we do the calculations further, and you see the curves here, this is the failure density function. Yeah, failure density function. Yeah, you see that q of t is 1 minus e to the power minus lambda t. Yeah, and the failure density function is lambda e to the power minus lambda t. So at t equal to 0, it will be lambda, right? At t equal to 0, it will be lambda. So that's what it is. At t equal to 0, it is lambda, and then slowly, exponentially, it is going to 0. Failure rate function, constant. Failure rate assumed to be constant. Yeah, hazard rate lambda t is equal to lambda. And the other curve is the cumulative failure distribution curve, which goes from 0 to 1. That is q of t, right? We have already established that earlier. Now we can integrate by parts and all that. So I just want to tell you that you will find that the mean is equal to 1 over lambda, the mean of a exponential distributed process. So this mean is also called the mean time to failure, and MTT by the small m. Yeah, we use little m to indicate that. Maybe somewhere else I have written it, but we use small m. And for repair rate, we are going to use mu. So we have m and we have mu, and the repair time will be described by r. Yeah. So the mean time to failure is represented by this equation, 1 over lambda. The mean time it will take for the component to fail once it is operating at time t equal to 0. That's what it really means. Yeah. 1 over lambda. So imagine if there is lambda is 1 failures per year. So then what is mean time to failure? If lambda is 1 failures per year, then what is the mean time to failure? 1 over 1 is 1 what? 1 what? Remember I told you lambda is 1 failures per year. So what is MTTF? 1 year, right? 1 year. That is 8,760 hours. So the component is failing after 8,760 hours. That's pretty reasonable. If the component fails after 5 hours, 10 hours, we should be worried, yeah, especially in power systems, right? So this is very common. Lambda, you will find in some of the calculations that we'll see later, 1 failure per year, 2 failures per year. And you will find mu, which is the other side, the repair rate. You will find mu is a very large number. Lambda is a very small number, but mu is a very large number. For example, if I say mu is 500 repairs per year, what does it mean? It means that if the component fails, I can repair it at the rate of 500 times in a year. That means I can repair it very fast, isn't it? So that's how it should be. Lambda is a small number, mu is a large number, which tells us that we can repair it very quickly. And the failure rate being small means it doesn't fail very often, right? So those are the systems that we want if we want a highly reliable system. Okay, so that's about the exponential distribution. Now, in brief about the normal distribution, which is also known as the Gaussian distribution. And the probability density function of the normal distribution is perfectly symmetrical. I think if we see this distribution, everybody is familiar with this. I don't know about your university, but in my university, when they have exams and when they mark the exams after that, everybody is fit into this normal distribution. Probably it's the same, right? Yeah. So it's throughout the world, I suppose. That's why normal distribution is so important. Everybody believes that we can fit everybody between the -3 plus 3 standard deviations, right? Because 99.6% or something like that data can come between these plus minus 3 standard deviations, okay? Plus or minus 3 standard deviations, yeah. I mean, you can go further, but really it's, no, not 6. We don't say 6. It's minus 3 standard deviations here, plus 3 standard deviations here. And this is the mean.
This is the mean. 6 sigma. Suppose I say, this is the, 6 sigma from the mean point of view. Then add the 6 times of that standard deviation, that's why.
Yeah, but.
He requires some, error in a million, they come out.
Right. We don't go beyond 3, but yeah, you can go more than that. Because this is a symmetrical distribution. It is symmetrical with respect to the midpoint. Yeah, that's why we talk about minus 3 plus 3, not 6. Yeah, but you want to look from this end all the way to the other end, yes, it becomes 6. Okay. Yeah, well, depends upon your outlook, I suppose. This is the Q of t, which we saw earlier. Q of x always goes from 0 to 1. Yeah, and this is the failure rate, lambda of x. In this case, as you can see, it's not constant. Remember, for the exponential distribution, we said lambda t is equal to lambda, and it's a constant. I showed you the curve. But here the lambda is different. Yeah, normal distribution is not a constant. That's why we cannot use the normal distribution to describe failures. Failures are exponentially distributed. But we can use this distribution to describe repairs. Yeah. Okay. So again, this is just to show you a bigger picture of this normal curve, and the area under minus 1 standard deviation or plus 1 standard deviation is 34%. So minus 1 to plus 1 standard deviation, you are considering almost 68%. Yeah. And if you go to minus 3 to plus 3, then you can see that the tail end is very, very little. You can consider almost 99% or slightly more of all the data. Right? So we are going to use this normal distribution, and these numbers will then come into play when I talk about generation capacity, reliability, evaluation. I'll give you an example where the load forecast uncertainty is described by this normal distribution. Now, in power systems, we forecast the load, don't we? You are going to forecast the load 10 years down the road. Can you be very certain what you are forecasting? There is obviously some uncertainty with the forecast load. Are you going to describe that uncertainty by a single parameter or by a probability distribution? We normally use the Gaussian distribution, a 2-parameter distribution, right? So we'll see that example when we get to that stage. Again, these are a little bit more specifics. The variable z in the normal distribution is described like this, and f of z is described by this equation. But this is all that is of interest to us. Plus minus 3 standard deviations, you capture 99.72% of the data, right? Now, these are the z tables that I'm sure everybody has seen before. Yeah. So you can see that when z is 0, then this is 0, and when z is 3.4, then it is 0.4997, almost 0.5. Right. So these z tables we'll probably use when you calculate something using the normal distribution. But for now, I think I've just put it there in the notes, just in case you need to refer to it. Okay. So you don't have to look for a mathematics book or something like that. Okay, any questions so far?
So higher the value of z, does it indicate that it is going far away from the mean value? Right?
Yeah, correct.
Going towards unstable.
Yeah, towards the extremes, yeah. Okay, so now we have studied the exponential distribution and the normal distribution. I'm going to use the exponential distribution and go back to what we call as time-dependent reliabilities. In the morning before the tea break, we said that we are using reliability of 0.9, 0.8, right? That is time-independent. But now we are dealing with reliabilities that can change with time. So therefore, we need to consider time-dependent reliabilities. So we go back to our old series systems, parallel systems, and see how we use the exponential distribution. So the reliability of a two-component series system, of course, we know it is RA, RB, but we now use time-dependent probabilities. So RA is RA as a function of t. RB is RB as a function of time, right? So this will be my system reliability. Everything is now a function of time, that's all, but still the two reliabilities get multiplied. And of course, if the failures are exponentially distributed, I can argue that RA is e to the power minus lambda a t and RB is e to the power minus lambda bt. Yeah, so these two can be combined. Therefore, we find that the equivalent failure rate of the combined system where two components are in series, the equivalent failure rate is lambda a plus lambda b, right? So this is the equivalent failure rate. So if I have got more than two components in series, then it will be lambda a plus lambda b plus lambda c plus lambda d and so on, right? So that is why we have this summation sign. And the overall reliability is e to the power minus lambda e, where e stands for equivalent. So I just use that e to mean equivalent component. The equivalent component series of two components or more in series is lambda e, where lambda e is given by this expression. So the effective failure rate containing components whose reliabilities follow exponential distributions, yeah, is given by this expression. The expected value, now what about MTTF, the mean time to failure? We are also interested in that, the mean time to failure. So the mean time to failure, we use this expression, the average value 0 to infinity TF of t, and if we do that calculation, we'll find that the MTTF is equal to 1 over lambda 1 plus 2 plus lambda 3. So the mean time to failure is 1 over the summation of the failure rates of the individual components. Yeah. This is a very significant equation which we very often use, yeah, in repairable systems, especially where exponential distribution is applicable. Okay. So here is an example of an electronic circuit. Consists of 6 transistors and 4 diodes in series. Find the equivalent failure rate and the probability of the system surviving 10,000 hours. So equivalent failure rate, because they are in series, it's very easy. 6 transistors and 4 diodes, so we can actually sum them up. And then the system is operating for 10,000 hours. What's the reliability? E to the power minus equivalent failure rate times the time. So equivalent failure rate multiplied by 10,000 hours, so we get 0.92. Okay. Fairly reliable, even though 10 components are in series, 92% reliable. And why is that? Because these values are so small, 10 to the power minus 6, 10 to the power minus 6. Imagine if those values are bigger, then obviously your system reliability will be much lower. Okay. Go to parallel systems now. So parallel system, we know Q is equal to Q1 times Q2 or QA times QB, but now they are time dependent. So 1 minus RA times 1 minus RB, and of course we have seen this equation before earlier today, and now we put everything time dependent. So QAT times QBT, which is this, which will be RAT plus RBT minus RAT times RBT, right? Yeah, same equation except that we are using time dependent probabilities. And since we are assuming exponential distribution, this R value is e to the power minus lambda t. That's all. That's the only change. So for n parallel components, the general equation will be Q is multiplication of all the Q's and R is 1 minus the total Q, right? So same equation again. And therefore, we can find that the MTTF of this distribution for a 2-component parallel system reduces to this form. And you find that now this is not exponentially distributed. So when 2 components are in parallel, the equivalent failure rate, yeah, or the mean time to failure is non-exponential. The resultant system reliability cannot be described by an exponential distribution. because it doesn't have an equivalent lambda, that is lambda A plus lambda B, yeah, but it is described by this particular expression. So the MTTF will be more complex if there are more elements in parallel. This is only for 2 components. If there are more, then the expression will be much longer. Another example here, reconsider one of the previous examples and assume that 2 such identical circuits are connected in parallel. This is the example of the 6 transistors and 4 diodes, remember? Yeah, we have done this earlier. So we calculated the lambda equivalent for one system of 6 transistors and 4 diodes to be 8 times 10 to the power minus 6. So we are using the same system, except that now 2 of them are connected in parallel. So lambda for one circuit is 8 times 10 to the power minus 6. For the second one is also the same. Since they are connected in parallel, the reliability is Ra plus Rb minus Ra times Rb, which is e to the power minus lambda At plus e to the power minus lambda Bt minus this thing. Of course, both are identical, so these 2 become 2 times e to the power minus lambda plus e to the power minus 2 times lambda t. Yeah, fairly straightforward mathematics. And then you can substitute the lambda. Yeah, the lambda was calculated as 8 times 10 to the power minus 6, and the time t is again 10,000 hours. So we put those numbers in and we find that the reliability is 0.994. If you compare it to the previously calculated reliability for that series systems, it was only 92%. Yeah, and now it has improved to 99.4%. So that's expected. I mean, we have quantified it. We were expecting it to be higher anyway when we connected elements in parallel, but now we are able to quantify it, right? So series, parallel, and now partially redundant. Parallel is fully redundant. Now we also need to know how we deal with partially redundant systems when we have time dependent probabilities. So in this case, we can use the binomial distribution, yeah, since r plus q to the power of n can be expanded directly, yeah. So for instance, if there are 4 identical components and it is a 2 by 4 system, then we can directly use r plus q to the power 4. Remember, in one of the exercises I told you r6 plus q6 square multiplied by r7 plus q7 square. So this is just the same, right? R plus q to the power of 4. If there are 4 elements in parallel, then you expand this, and if it is a 2 by 4 system, then you choose the terms which are successful. So this one is a success. Why? All 4 are operating. This is a success. 3 of them are operating. This is a success. 2 of them are operating. This is a failure. This is a failure. So you can throw the last 2 terms away and your reliability is only the first 3 terms, correct? 2 by 4. If I make it 3 by 4, it's different. Yeah. 1 by 4 is fully redundant, right? So for non-identical components, this is for identical. Binomial you can only use if the components are identical, right? If they are non-identical, what do? Then you have to go the long way. R1 plus Q1 multiplied by R2 plus Q2 multiplied by R3 plus Q3 and so on. And then pick the good terms. Good terms meaning at least 2 of them have R. Yeah. So that will be slightly longer if it is not binomially distributed. So another example for you here, similar to the type that we have seen before. We've got components 1 through 6. This is a 2 by 3 system. This is a fully redundant system. Given the lambda of each of these components, calculate the system reliability for a mission of 5,000 hours. Yeah. So I'm sure everybody can do it. 2 out of 3 system, we know how to do it. R4 plus R5 plus R6. You have to find the good term. So R4 plus Q4 multiplied by R5 plus Q5 multiplied by R6 plus Q6. Expand. And then look at the terms where there are at least 2 R's. Yeah, that will give you the reliability of this system. How do we calculate it? Reliability is e to the power minus lambda t. Okay. And then for this system, fully redundant, R2 plus R3 minus R2 times R3. And then this and this and this are in series. So multiply the 3 reliabilities. So we know the process. You just need to plug in the numbers And that's what I have done for you over here. Okay. So instead of using a number which we used before the tea break, now we are saying that the reliability is exponentially distributed. So instead of R being 0.9, now it is e to the power minus lambda t. Yeah. So lambda is given to you. So you need to know the mission time, and then you can calculate the reliability. Otherwise, it will be in the form of lambda if you don't know the time.